Get started. All right, how's everyone doing? Good. It's a week after the midterm. Midterm grades were released yesterday or 2 days ago, and yeah. So overall, I thought our section did pretty well. Yeah. So and then this includes SCPD students as well. So good job to all of you. Um, what I found just by looking through your exams is we're pretty good with read questions. Yeah, we're pretty good with read questions. Write questions, pretty good, although we could use a little work on those. So what I think I'm going to do for the last couple sections is rather than do like tracing problems, I'll do more coding questions. Is that all right? Okay. Yeah. All right. Awesome. Then yeah. So just some quick announcements. Assignment 5 was due yesterday, but if you use a late day, you can need to turn it in tomorrow. I highly suggest, even after you turned it in, double check by running your program again and just making sure you haven't missed anything. The most common source of error on this assignment is you think it works, but you never actually tried everything to make sure that it actually does work. Okay, cool. Assignment 6 will go out on Friday, and I don't know, it's probably around as tough as assignment 5. So depends on how you think on assignment 5 was. Okay. Cool, cool. So this section is going to be about pointers and linked lists, and this has historically been my favorite section, often because I love drawing diagrams, and today we're going to be doing a ton of diagrams. Okay. The key thing to know about when you do these types of problems is you need to always draw a diagram because that will tell you exactly what to be doing with each of the pointers. Okay. We call this like pointer gymnastics, and essentially you just have to visually see which pointer you are changing at each point. Okay. All right. I want to share a quote, and so some of you asked me this during IGs, and I think it's a really good point. Why are we learning linked lists? They seem like just a worse version of a vector, right? Kind of. Yeah. I had a friend who took this class last quarter, and he told me something very insightful that I thought was really cool. Basically, you can think of everything in CS. Everything really is really just a glorified linked list. Okay. Yeah, because I'll give you a couple examples today that what we will often see in computer science is you'll often see that everything can be kind of modeled like a linked list, and the structure of a linked list is really nice. Okay. Um, how many of you have heard of heap allocator from 107? If any of your friends are in 107, they'll probably have heard of heap allocator. If we have time later, I'll try to explain why linked lists are used, why they're not just this artificial thing that we come up with. Okay? Cool. Okay, so let's get started. Before we go into linked lists, I want to quickly go over this thing called big O notation because this is Marty usually puts this before on the midterm, but I think he's going to do it on the final this time. Usually there's going to be some sort of question where you're given a piece of code and you're going to be asked very simply, what is the big O runtime complexity of this piece of code? Okay. So do we remember big O? I think it was like before the midterm, so maybe we skipped it. Or did y'all go to the lecture that day? Big O notation? Okay, if not, let me just do a quick overview, 1-minute overview. Essentially, the idea is we try to quantify the running time of an algorithm. Now, you can't really calculate the exact number because if you run the same program on different computers, depending on how good each computer is, they might have different running times. So the key idea is rather than focus on exactly how fast it goes, we want to think about how the runtime grows as n increases. Okay? So for example, in a code, some really common complexity classes you'll see are these. N log n, O of n squared. And then you'll often see something like 2 to the n, and then O of n factorial. Okay? Yeah, so these are some of the really common complexity classes you'll see. The idea is O stands for order of. So if your program is O of n, that means if n increases, then the runtime complexity grows linearly. Does that make sense? So for example, if in an O of n program, if you double the size of the input, suppose I change from size 100 array to a size 200 array, then my runtime grows by the same amount linearly. Okay, as opposed to like an n squared algorithm where if you double the value of n, how much does the runtime grow? 4 times, right? If you double n, then this expression goes up by 4. All right, that's the key idea of runtime complexity. Now, to figure out what the runtime complexity is, you can often just take a look at the code and try to figure out essentially how many times the program is running in response to the value n, or usually it's the size of some vector. Okay, so for example, let's take a look at this program over here, count distinct 1. So the key idea of all 3 programs is they're trying to count how many distinct integers are in a unsorted vector. So you're given a vector like 1, 2, 2, 3, and essentially you want to try to count how many distinct elements there are. So in this case, there would be 3. All right, all 3 of these work, but some of them are better than others. Okay, so you can take a look why. Let me pass out the handouts. Here you go, handout. And it's question 1. So take a look at question 1 and think about what the runtime complexity is. All right. So looking at the first way of count distinct 1, can you just give me a quick idea, like what is this algorithm trying to do essentially? How is it trying to find how many distinct integers there are?
It goes and like compares to all the values it's seen before, basically.
Yeah,
Each
yeah.
element it compares to all the elements before it.
Yeah, exactly. So the idea is given like some sort of array. 2, 3, 4, 4, 2. All right, what it's doing is it's going through all the elements. That's the first for loop out there. And then that's this for loop out here. It's going through all the elements. And then after it does that, then it goes through all the elements before the element. So for example, at 0, there are no elements before. So we don't check the elements before. When you go to 1, then you check all the elements before this element. When you go to this one, you go check all the elements through here. And what happens when you check through the elements? Suppose we were here, and then we were just going through these. What are we doing at each step?
Like checking if it's true or false.
Yeah, so we're checking if any of these match this one, right? Because if any of these match this one, then this one is not distinct. So we just don't count to that. Okay? So intuitively this works, right? We're just going through all of them, seeing if any of them have appeared before. If they have, then don't count it. Otherwise, count it. Okay? Now, why this is interesting is because runtime complexity-wise, this, let's think about the runtime of this. Okay? So if the size of this vector was n, how much time are we have to go through all n elements. Okay? At each element, let's say we were at this point. How many elements do we have to check at this point in the for loop?
2.
We have to check these 2 elements, right? So think about it this way. We're going through the entire vector. At each point in the vector, we're essentially double checking if this one matches any of the elements before. Okay?
Yep, adds up.
Yeah, so if we were at the first element, how many checks do we have to do?
0.
0, right? Okay, so first element, there are 0 checks. Second element, 1 check. Third element, 2. And you can imagine that it goes all the way up, right? Okay. And it goes all the way up to what?
N minus 1.
N minus 1, okay? This is not being super precise because we don't actually know how much time it takes to check each element. But you can see that the first element has to check nothing before. The next one has to do 1 check, 2 checks, 3 checks, all the way up to n minus 1 checks. And this happens n times. Okay? Now, so if this is our total runtime, how can you write this in terms of one of our complexity classes? This should remind you of some formula that you might have seen in high school, I guess. So quick question, is this expression on the order of n log n log n squared? Which one is it?
N squared?
N squared. Well, why n squared?
Well, it seems like you're doing.
Yeah, you're exactly right. So one way to think about it is, well, you have n elements, and each one goes up to n. So this is at most n squared, right? The other way you could do this is there's also a formula, which is the sum of the first n or n minus 1 integers is like n minus, I think it's, correct me if I'm wrong, I think it's this. Something like that, right? This is the formula. And then if you wrote this, if you expanded this out, this would be 1/2 n squared minus 1/2 n. So remember, for big O notation, we just ignore everything, all the lower powers, and we just look at the leading coefficient, n squared. Does that make sense? Okay. This is usually the freebie question on the final, so make sure you know this. Okay. Cool. So this algorithm runs O of n squared. Let's look at the second algorithm, the count unique 2. Right? Look through it and think to yourself, what is its runtime?
Adding an element to a set is O
N.
Log n, yeah.
log n.
Yeah, O of log n. Adding an element to a set is runtime O of log n. I know this is kind of hard to remember, but the way to remember is for a map and a set, it's always log n. Later, you'll learn this thing called a hash map and a hash set. That's O of 1. Okay? The reason why it's log n, you will learn next week when you do binary trees. Okay? But yeah, so adding an element to a set runs in time O of log n. How many times are we running this command?
N times.
N times, because we're going through the for loop and we're just going through it n times. So what's the runtime of the entire algorithm?
N log n.
Yeah, n log n, okay? Because each element we're going to use log n time, and then there's n elements, so the runtime is n log n. Okay? Yeah. We can do the similar analysis just by looking at the loops here. How much time does this loop spend? This loop over here. Oh, yeah? Mm-hmm. Okay, yeah. So this is just a easy trick you can do on like the exam or something. If whenever you see one of these, like if you have 2 for loops and then the inner for loop uses a variable, the counter from the outer for loop, the way you can solve these questions is basically take the bound of this variable out here and just plug it in, replace it with the I minus 1 here. So let me quickly explain, okay? So I goes from 0 up to n. So whenever you see a bound I minus 1 here, you can just replace it with n. Okay, that will computationally do the trick every time. So here, we can imagine there's a for loop out here that goes up to n, and then this inner for loop also goes up to n. Okay, so you're running an O of n. It takes O of n inside the for loop, and you're running the for loop O of n times, so it's O of n squared. Okay, the trick is to always take the counter variable and just every time you see that counter variable, replace it by its upper bound, which is just take the I minus 1 here, replace it with n. Does that make sense? Okay, yeah. Sometimes Marty tries to confuse you by saying like, oh, the outer loop goes up to n, the inner loop goes up to like I, the inner for loop goes up to I times j or something, and then just the key way to remember these is just every time replace the bound, replace that counter variable with whatever it's bounded by. Any questions? Okay, so my question is, if this algorithm is n squared and this algorithm is n log n, then which one's faster?
Number 2.
Yeah, n log n is faster. All right, because if you do like the comparisons, n is smaller than log n, so n squared is smaller than. N is greater than log n. My bad. So n squared is greater than n log n. Okay, cool. All right, we're almost done. Let's just look at this final one, mystery sort. So quickly look at the third one and try to figure out how it's trying to solve the problem. Convince yourself that it works. Yeah, could someone just give me like a quick 2-sentence explanation? Why does the third one work?
Because they sort the vector before going through it. So you can element by element, and the one before it will be, if it's the same, then it will. Then you can add it.
Yeah, exactly. So we're essentially taking this vector and we're just first sorting it.
And gets rid of all the copies that are next to each other.
No.
No, but it doesn't count. So it's like you have 4 or 5 of them. It just only takes one.
Yeah, I see what you mean. So the vector doesn't actually change, but as we're counting them, if they're like repeats, then we just don't count them, right? Because the same element's going to be next to each other when you sort them, so you can just go through them and count how many times you change the number, right? So we start with 1, we go up 2 to 3, 3 to 4. So 1, 2, 3, 4, 3 elements. Okay, cool. So this works. Let's just try to figure out its runtime, okay? Before we think about the mystery sort, let's look at this expression in here. What's the runtime of that expression, of this for loop? O of n. Why is it O of n?
Going through once up to the size, which is n.
Yeah, exactly right. So you're just going through the entire vector, which has size around n. It's n minus 1, but remember the smaller terms don't matter, so it's just O of n. And then each of this if statement is constant time. So this takes O of n. Now, mystery sort. We don't really know what mystery sort is, but suppose mystery sort was insertion sort. Remember what insertion sort was? Okay, I'm not going to go over insertion sort in Drewing section because we want to cover linked lists today, but review insertion sort. It's an important sorting algorithm. Anyone remember what its runtime is? Okay, it's O of n squared. Okay, so insertion sort runs in O of n squared. So if insertion sort runs in O of n squared, what's the big O of this entire algorithm? O of n squared, right? Why is it O of n squared?
Because they add up n squared plus n is n squared.
Yeah, exactly right. Okay, this is a common thing to think about is when you have 2 pieces of code which run sequentially, like the first piece runs first, then the second piece runs later. It makes sense that the running time of both of them is just 1 added with the other one, right? Okay, yeah. So because we have an O of n squared here and we have an O of n here. When you add them, when one runs after the other one, we just add them. And when we add them, n squared plus n squared is larger, so we just keep the n squared. Okay? What if it's merge sort? So remember merge sort?
Yes.
What's the runtime of merge sort?
It's fast. It's n log n.
N log n, yeah. The merge sort is n log n. All right? So if mystery sort is n log n, then what's the runtime of the entire thing? N log n, because n log n is still larger than n. Okay? Key thing to remember is when you have code sequentially, you add the runtimes. When you have code that is one is nested in the other one in terms of a loop, then you multiply them. So in this example, the outer loop was n, the inner loop was n. So because one is nested within the other one, it's n squared. Okay. Okay. Before I move on, just wanted to warn you of one thing. Okay, this is like the most missed thing on the exam probably. Suppose you had a vector. Okay, and then there's some code that you don't know. Then you see this operation v vec dot insert. What's the runtime of inserting? Let's just put 999. What's the runtime of inserting an element at index 2?
N minus 2.
N minus 2, right? Because, yeah, you're exactly right. Because in our vector, all right, suppose we had 1, 2, 3, 4, 5, 6. Suppose we wanted to add something at index 2. How can we add something at index 2? Well, we have to move each element down. Right? Every time you move an element down, that takes time. How many elements do you have to move down? N minus 2. Or the idea is the runtime of this is just O of n. What is vec dot? What's the runtime of add? O of 1. Why is it O of 1? Yeah, we just add it at the end, so we don't have to shift anything down. Okay, now this is tricky. This is very tricky. What if we wanted to add an element at the second to last element, at the second to last index? What's the runtime of this? So I see 2.
Oh, what?
Yeah. So you have to move 2 elements, right? No matter what the size of the vector is, how many elements do you move? 2. Okay. Because it does not depend on n, the runtime of this is O of 1. Yeah. It's constant time. This is the most missed thing because some students think, oh, vec.add is always going to be
Since it's a
linear.
constant, you just say like O1 instead of O2.
Yeah. So yeah, remember for big O, we don't care about what the exact coefficient number is. We just care about what power or what order of magnitude it is. Okay. So it's just O of 1. Yeah. So the key thing is on the cheat sheet, you'll see that vec.add has a runtime of O of n, but that is if you put a constant in here, like a constant index from the front. If you add it at the back, then the runtime is O of 1, not O of n. Right? Key things to think about. Don't just blindly memorize these formulas. Try to understand why this is O of n so you won't get tripped up by these. Okay? Cool. Let's go to linked lists. Okay. We don't have a lot of time, so I'm not going to do a review of linked list, but I'm going to assume we know what pointers are. Yes, we know what pointers are. We know what structs nodes are. So we'll just quickly do one of these. This is a very classic 106B question, which is given a linked list like the one shown up here. So this is the before diagram, 5, 4, 3. Change it using pointers to get to this after diagram, 3, 4, 5. Does that make sense? Okay, and then the rule is you cannot just go in here and change the values. You have to change the pointers so that it becomes 3, 4, 5. Does that make sense? Questions so far?
Can you repeat that for me?
Yeah, sure. So the goal is we want to take this linked list, which is just this, and we want to reorder it so that it becomes 3, 4, 5. Okay, we're not supposed to actually go inside each of these nodes and change the 5, the 4, and the 3. Instead, we want to change the pointers around, change these arrows, so that the order becomes list goes to 3, then goes to 4, then goes to 5. Does that make sense? Okay. Okay. Let's imagine how would you move the pointers around?
First move the 5, make the address where 3 points to be that 5 and have 5 as address,
Okay, so let's see. So the first thing you want to do, did you say 3 points to 5? Okay, yeah. All right. So remember, each of these are addresses. Should I explain pointers, or are we familiar with pointers? Yeah, I usually want to spend more time on pointers, but the thing is then it's more like a read question, so I kind of want to go into more code writing. Is that okay? Okay, yeah. I usually spend a lot of time explaining pointers and how to think about them, but I really want to do one of the more complicated examples. So each of these are addresses. They're addresses to where the next element is. So we can think of this as 0xAA, 0xBB, 0xCC. You can think of each of these pointers as an address to the next one, 0xBB, 0xCC, and then this is just null. This first one is also a pointer, so it also contains an address. And it tells you the address of the first one. Okay? The idea is we want to go into each of these pointers, each of these nodes. Each of these nodes has two fields, a data field and a next field. The next is the pointer. The data is the actual int value. All right, and then we want to. Usually we don't write it like this. Usually we just write it as if we just draw arrows to represent the pointers. Okay. So then, so you mentioned you wanted to turn 3, and we want to make 3 point to 5. Right? How can we write that as code?
Use a while loop to kind of have some temporary thing point to something until that item's next is a null pointer.
Sure. Yeah, we can use a while loop here. We're gonna use a while loop later when we do like examples where you don't actually know how long the list is. Right now we're just doing some simple pointer practice, so we actually know exactly this list is gonna be 3 elements long. Okay, so we're not gonna use a while loop here. You can definitely use a while loop, and when you don't know how many elements there are, you have to use a while loop. Okay, but otherwise, let's just write it as if we didn't have a while loop. How would you change this pointer to 0.25?
Next.
So you said the list next.
So that's pointing to the item with 3 in it now.
Okay, so let's think about what list next means. Okay, remember this the arrow notation. The arrow notation is equivalent to dereference, which means follow the pointer to where it's pointing, and then access the field. So list next, just this part, means list, follow the arrow, and access the next. Okay? So what does list next give you? Yeah, so list, the arrow means follow the arrow, and the access the field next. So this part gives us this. And then we're saying arrow again, which means follow the arrow, and get the next component, which is this. Okay? So this thing is referring to this arrow, this field up here. Right? Is that what we want to change? We're trying to change that one, right? Yeah. So you're really close. You just have to go one more layer down. All right. So list next. So the way to think about this is list next. This part gives you the 3 node 3. Right? If you think about it, list. Remember that list is this one. Don't start here because there's no point. There's no node here. List next. List next gives you node 3. And then what we're saying is we want to take node 3 and we want to change its next field. We want to change its next field to something else. What are we trying to change it to? To 4? Okay.
So list next.
List next. Let's see. 3, 4, 5. Sure, yeah, we can do that. Okay. You said 3 to 5. We can do 3 to 4, 3 to 5. It doesn't matter. As long as you end up linking everything else, that's fine. Okay. So let's think about what this does. List next. This is referring to node 3. We want to change node 3's next field to list next. Actually, list next. Well, what does list next give you? Is it 4? List refers to this one. List next refers to this one. List next refers to this one. So this refers to node 3. Which is this, right? This refers to node 3.
Wait, how are they referring to the same thing?
So remember that this component is saying node 3. This part means we're looking at node 3, and we want to change its next. node 3 is next to something. So this is node 3. This is the next component of node 3. Does that make sense? So this is node 3. This is also node 3. But that's not what we want to do, right? Yeah. Yeah, we just want this one, right? This is just referring to 4. Yeah, exactly. Okay, I know this is confusing, and the most common mistake on this one is you're like off by one next. You're off by one layer of next. The way to think about it is this is on the left-hand side. The last next is referring to the next thing that you want. Is referring to the next pointer that you're trying to change. You always look at everything other than the last one. This refers to which node you want to change. And then you say that node's next is what you want to change. In this example, node 3's next pointer is what we want to change. Node 3's next pointer. Okay? But on the other side, then we don't do this like one-off thing. List next clearly just refers to 4. All right?
Yep.
Cool. Okay. What's next? Next.
So now we want list next to refer to list.
Okay, so let's see. List.
List next.
Okay, sorry.
Oh yeah, you're right. You're
Yes. Okay, list next to refer to what?
right. List. The list.
List. Okay, yeah.
Uh,
So good catch there, because this part, list next is node 4. And then we're saying change its next pointer to
Yes,
list.
yes, yes.
Okay, cool. All right. One small issue here. What issue do you see right now?
you've lost 3. You don't know where it is now.
Yeah, notice that we can't access 3 anymore.
You gotta make it temporary, huh?
Yeah, exactly. We have to make a temporary pointer. All right. So a temporary pointer is essentially you can declare another pointer just like this one. We're just going to create another pointer here. Temp.
And down.
We're going to just point it to this one. Okay. How do you declare temporary pointers?
You just say temp equals fucking. I don't even know.
So let's assume we haven't changed this one. We still had this. Right. How do you set this to this node over here? What's the address
Just
of
create a new
Next.
list node with that value.
Yeah, so we're not actually creating a new list node. A new list node would be creating a whole new node. Right? We're not actually creating a whole new node. We'll do that later.
Oh, list next.
List next, yeah. Here we're only dealing with, these are all addresses. These are all pointers. Okay? Temp is equal to list next. Okay? So list refers to this address, this node, this address over here. Remember that list is an address, right? The address of list, no, so list itself contains the address of this node, 0xAA. When we say list next, it gets us this, whatever is in here, which is the address of 0xBB. And then we do next one more time, we're getting this address. So this is the third. Now, you notice I left a blank here. It's because this is a new variable. We have to declare it. What is its type? What's the
Pointer
type
to
of?
integer.
Hmm?
Pointer to integer.
It's a pointer to a list node. Each of these is a list node, remember, okay? Yeah. List node. And how do we declare a pointer? Yeah, exactly. Okay. Any questions about this? So we have temp, and then we do list next equals list. That changes this pointer to here. What's next?
Now we gotta put
Next is
temp.
temp.
Yeah.
Okay. List equals temp.
And we also need to change the 5, the end of the 5 to be a null.
Yeah. How
we
would you
might
write
have
that?
done that before, actually. Maybe that's.
Yeah, there's a reason I left a little space in here.
Yeah, that's
Um,
good before.
What's the code to change? Remember that we have to change this pointer to the null pointer. How do you change this to a null pointer?
List next is null.
Yeah. List. Okay, important. remember that this one refers to node 3, and you're saying change, no, this one refers to node 5, change 5's next pointer to null pointer. Okay? And then what does list equals temp do? Okay, so, go ahead.
It just takes that value temporary and then it just overwrites the memory.
Exactly, yeah.
That list of 3.
Super important, list equals temp does not change what they are pointing to. List itself is a variable which has an address in it, 0xAA. Temp itself is a variable with address 0x, which has an address in it, 0xCC. When you say list equals temp, you're saying, okay, list, I want to set the value inside list to equal that one inside temp. So this becomes 0xCC. And what does that do in terms of this diagram over here? It changes this arrow to over here. Not there. To 0xCC, which is this one. Okay. Now if you look at our list again, list points to 3, which points to 4, which points to 5, which ends. Does that make sense?
Out of curiosity, what would happen if you put ampersand list equals ampersand temp?
Ampersand list equals ampersand temp. Let's see. So do you remember what ampersands are? Or what they do in terms of pointers? Okay, yeah, that's a good question. Let me write that out. So the question was, what happens if you do something like this? You're saying ampersand list equals ampersand temp, right? Okay. I don't think this won't compile, actually, but let me just quickly explain what ampersand temp does. What does ampersand temp do? Do you remember what ampersand does? Ampersand gets, if you put ampersand next to a variable, this is different than the pass by reference, okay? Putting an ampersand next to a variable, it gets you the address of that variable. Okay, so temp itself, this variable is stored at some address 0xFF. Okay? So if you do ampersand temp, you'll get 0xFF. Okay. Now the thing is, ampersand list also gets you the address. But the thing is, this is not a variable. You're not just allowed to randomly go into a variable and change its address. Okay, so this won't compile. Okay, if you want to take 106L, which is offered in the fall, we'll talk about this thing called R values versus L values. If you've written some code, you'll notice that sometimes you get the error like you can't assign R values to L values. Have you seen that error before? Okay, if you haven't seen it, you will see it soon. Yeah, essentially the idea is you can't set this thing, which is called an R value. It can only appear on the right. You can't put that on the left. Okay? This example is not super important because this is a non-example. This won't compile. You can't do this. Okay? But you can do list equals ampersand temp. How is list equals temp different from list equals ampersand temp?
Now becomes a pointer to the pointer temp.
Yeah, exactly. Okay, this is super kind of janky. So if you do list equals temp, what it does is it copies whatever is in here into here. If you do list equals ampersand temp is the address of this variable, which is 0xFF, and you put that into here. What happens is then what this becomes 0xFF, and it points to this address instead. It points to this variable. Now, I don't think this compiles because this is now, what's the type of this thing? This is a pointer to a pointer, okay? You declared temp as a regular pointer. This is a pointer to a pointer. So this won't compile, but this is essentially what it would do. If you take CS107, that's where you'll see pointers to pointers to pointers. Okay, fun stuff. But we won't cover that here. In this class, you only have to know regular pointers. All right, any questions? So there's another part B. I want you to all, sometime today, practice part B, okay? It's relatively short. It's as long as, 5 lines of code. Just write it out and double check your answers, okay? How are we doing so far? Notice everyone is a little bit distracted. How are we doing? Does this make sense? Is there something I should explain further? What's the confusion right now? What questions do you have?
This might just be another non-example, but what if you do star list equals star temp? Would that change the things that you're...
Interesting. Star list equals star temp. Okay. Anyone remember what star does? Star dereferences, which means star literally means follow the arrow and get what is at the end of the arrow. Arrow is follow the arrow and then look at the thing that's at the end of the arrow, pick out that field. Okay? So if you do star list equals star temp, then what it does is it's saying star list, which is this whole thing, 4, set this whole thing to equal to star temp. Star temp gets you this whole thing. Star list gets you this whole thing. So star list equals star temp means copy this whole thing into wherever this thing was. Does that make sense? Star list equals star temp. That means star temp, follow the arrow. What's at the end of the arrow? This is star temp. Star list, follow the arrow. Find what's at the end of star. This is really confusing. Why is it written like this?
So it would be pointing to itself then.
Sorry, I think I'm getting the other way. So list, star list. Okay, I'm going to get rid of this example. Okay, this was pointing to here. Okay, so star list gives you this thing. Right? List is this one, and then star list means follow the arrow and get what is over there. Star list. Star temp is follow. Oh yeah, get itself. Yeah, so you're just setting it yourself to yourself, which doesn't do anything. Okay, let me answer that question. If you have more questions about that, let me answer that later. I want to just do one more example, okay? And this is like a more typical linked list question. Okay, this is called insert. Okay, suppose you had a linked list which looks like this. Okay, so 8, 7, 9, -9, -8, -7. What I want to do is, actually, don't use this one, use this one. We have a linked list where each of the data is a string. So Marty, Julie, Kate. We want to write a function called insert, where if you do something like this, insert, or if it takes in the front of the list, it takes in some string, and it also takes in some index. Okay, and what it should do is it should go into this list and add Avery at index 2. So this is index 0, index 1, this is index 2. So what we do is we add a pointer here. Does that make sense? Okay, just as a final check, what happens if I do insert front Maron 0?
You want the stars.
Yeah, we added it at the front, which means do this. Okay? Does that make sense? Okay, how can we tackle this problem? So suppose we start up with this list over here. How should we tackle this problem?
So we want to go to next for predefined number of times.
Mm-hmm. So yeah, for the first one, for example, you want to first go to where you want to add the list, right? Okay, where would you go?
I go to next.
Okay, so you'd go here, right? Which is right before where we want to insert. Okay. Did Marty use the James Bond analogy?
Good thing.
Okay, yeah. So the James Bond analogy is this: if James Bond was going here and he wants to remove, or he wants to remove like a suppose he was on some sort of train, like if the trains were connected like this and he wants to remove this train off from the rest of the train, you have to go to the one before before that to be able to change this pointer. The idea is you want to keep moving down until you get to right before where you want to change. Right? You can't just go here, because if you're here, you can't change this pointer. You have to be here to change this pointer. Okay? This is really common in linked list questions where you're going to essentially loop over the entire linked list. And then at each element, you either process it or you do something with that. Okay? Does that make sense? Okay. So we're going to essentially find where we want to go. Let's say we had a curve pointer, which pointed to here. Suppose we found where we wanted to go. How can we add a new item into our linked list?
Well, maybe we actually first want to add like Avery and have it pointing to Kate. Otherwise, we detach Kate again, and that's not great.
Yeah. That's a good point. So you're saying create. First, we need to create the node. Okay, so we're gonna have to create Avery first. Okay, so let's say temp points to here. And you're saying have this one point to Kate first. Okay, so we want to have this point to Kate first. What happens after that? Yeah, so we have cur, whatever's at cur, and have that point to Avery. That's how we do inserting, right? Make sense? Make sense?
Yes.
Okay. Let me try to. Let's code that up quickly. Let's see, list node, write code, here. All right. How are you feeling about this so far? I feel like some of you are a little confused. Are we going at a right pace? Okay, after section, feel free to ask me questions about this. This topic is really important because next week is binary search trees, which means same things about pointers, but rather than having one linear list, you now have branching. So it's like a link. It's a glorified linked list. It's a linked list which branches off into many other linked lists. All right. So I want to make sure we get this stuff done. Let's see. So let's first write some pseudocode. Never mind. Let's not write pseudocode. List node star front. Okay. Let's see. How could you solve this question? We want to first find where we would insert, right? Right, we need an index, index. Okay, so how do we find where to insert?
Index.
No one else need a value?
True. Okay. How do we insert? How do we find where do we insert the new node?
You need to use the while loop.
While loop, sure.
Count.
Yeah, so because you already know how many times you have to go forward, that's just index, so you can just use a for loop. Okay. How many times do you go in the for loop?
Index.
Index minus 1. I think that's right, yeah. Yeah. So we're gonna start at front. List node star cur is equal to front. We're gonna start at front and then we're just gonna loop down. We're gonna go forwards n minus 1 times. So here we go forward 1 time until we get to the node before where we want to insert. Okay. How can you move the pointer down?
Cur equals cur next.
Yeah, cur equals cur next. So cur equals cur next, what it does is it moves cur down by 1. And we're doing that n minus 1 times. Okay? Any questions at this point? Okay. So we move, cur is now pointing to Julie. What should we do next after cur is now at Julie? So let's quickly draw this. We don't have this thing yet, but we probably should. After cur is now at the node before we want to remove, what's the next step?
We want to create Avery and then have it point to Kate.
Okay, so how do we create Avery?
With the list node.
Yeah. Let's see. Temp. So we want a pointer, and how do we create the new node itself? New list node, exactly. Okay, and I think you can do something like this. We just create the value and no point. Oh, I think you can do this actually. Okay, so list node, when we call the constructor for a list node, I think there's a default constructor where if you put these two values in this order, then it just initializes it for you. Okay. The other way you can do this is you can, instead of doing this, you can say temp data is equal to index, not index, value, and then temp next is equal to what should Avery point to? Kate, right? And how do we get Kate? Cur next, exactly. Okay. So we can do this. I generally prefer just writing it here. Value cur next. Okay. So this creates Avery, and to access it, you use temp. Okay. Now, what's the last thing we have to do?
Have Julie point to Avery.
Okay. How do we do that?
So
Mm-hmm. Yeah.
Move the pointer after Julie.
Okay. Which pointer are we moving? We're moving the next pointer of Julie, right? Okay. How do we get that pointer? So we can get Julie using cur, right?
Yeah.
Yeah.
So incur.
Yeah. So cur gives you the Julie itself. Arrow next gets you the next pointer of Julie. Yeah. It's the same idea as what we did before, where everything except the last next is referring to what node you're changing, and then arrow next means take that node, take its next pointer, and change that. So what that does is we're saying, take Julie, look at its next node, and change that to point to whatever temp was. That equals temp. Okay? Okay, one final thing we have to talk about before we leave. This is, there's one thing missing here. Yes, okay. Right now, we actually don't need the reference because we're missing something. This won't work if we try to insert at front, if we insert at index 0. Right, because if we insert as index 0, let's see, then nothing happens here. And then we set the front next equals temp. So that inserts at index 1. Right? What's the difference between adding at everywhere else versus adding it at index 0?
You don't need to move the previous pointer. You just have to add it. And
Yeah.
you're going to move the next pointer of that.
Mm-hmm.
node.
Yeah, there's no previous pointer, but there is something you have to modify. Front itself. Right? Nowhere else do we have to actually modify front, except if we add it at the front. So you do want to check before you do all of this. If index equals 0, then what you actually have to do is when you create the new node, when you create this new node, you have to set front equals temp, or front equals temp. And then you also do the cur front next equals the next one, which is, actually you probably want to do temp next equals front. So that sets the new node, its next pointer. It goes to whatever is currently in the front right now. And then we set front equals temp.
So we'll move that cur next.
Cur next.
Just above.
Yeah. So then we won't have this thing down here, right?
No, but just above where after if index is 0.
If index is 0, okay.
Okay. Line 3, we set the new list node to the point of it.
Oh yeah, that's a good point. We can just put it front here. Right? We can just do this. Essentially, we create a new list node with some value, and its next pointer is pointing to the first thing in the list because we're adding it before the first element. Does that make sense? Okay. Yeah. So the key insight here is why do we need the reference here? Because you're actually modifying front. Okay. The key thing to note. Okay. Don't always just blindly add the reference here. Think to yourself, do you ever actually change front? Not what front is pointing to. Do you actually change the front itself? If you see, anytime you see front equals something, that means you have to pass it by reference. Okay, cool. final insight I want to put here is whenever you solve a linked list question, first do this part, which is like, in general, if you wanted to do something with the middle elements, what do? Then you want to explicitly think, what happens at the very front? What happens at the very back? Okay, because sometimes those are separate cases compared to adding it in the middle.
So do you have to do another case if you're adding it just to the?
Oh, sure. Yeah, if you have to leave, feel free to leave. But let's see, adding it to the back. I think it works over here because, like this case does it correctly because you have to. This essentially goes to the back of the list, the very last element, and then we're essentially just adding one element at the last element. Notice if we add it at the end, what is temp next equal to? Yeah. So because cur is the last one, cur next would be the null pointer. So if you add it at the end, that new node at the end, next pointer, will be null pointer, okay? Which is just conveniently correct, all right? Yeah. So this is going to be very common when you tackle assignment 6, which now I can imagine is probably pretty tough. Yeah, assignment 6 is you have to worry about cases like this, adding in the front, adding in the back, and so on, okay? Yeah. Assignment 5 in the past was adding. You had to do it 3 ways, including the heap way. But another way you had to do it was using a linked list. Okay, he decided to move it to assignment 6. Okay, so yeah, so thanks for coming. Let me know if any questions, and then I'll see you next week. We have 3 sections. We have 2 sections left after today. All right, thanks for coming.